David Thouless, who could show that these steps here actually can be explained as such a topological invariant. It's not exactly as the number of holes in a bagel or a pretzel, but it's something very, very similar. And this also explains why it is so precise, why it's so robust, why you get integer steps. And later on, 1988, Duncan Haldane, another of today's laureates, showed that you could do the same without having this very strong magnetic field. And for the continuation of this field, that was very, very important. Now, let's move on to the next concept in this citation, namely topological states of matter. Now, what is a state of matter? Well, this is something that you presumably know from school. If high temperature, you can have a gas. Lower the temperature, you get a liquid. Lower more, you get a solid. But when you lower temperature even more, close to absolute zero, there are new fascinating phases of matter. And the ones we talked about before, these electrons in a layer, that's such a topological phase of matter that you find at very low temperature. Now, this is not the only one. Haldane, in 1983, looked at another kind of system, a set of magnetic atoms in a chain, and he could show that even in this case, you had such an exotic topological phase of matter. And now, actually, the race is on, and you look for topological phases of matter in chains, in layers, but also in ordinary three-dimensional materials.